No, we're gonna.
Okay.
Yeah, we'll put them too hard. Like, yes.
Here we go. Give this one a shot.
I'll be there around. We're gonna watch
Folks. How many folks?
Oh.
I know. Crazy. Thumbs up when you have something. Tell your neighbor and tell them why.
You're actually because one's pulling you up. Yeah, one's pushing you right, one's pulling you right. Or we could just be wrong. But give me 0.
Correct answer is. Correct answer is A. What's going on between 1 and 2?
Pushing the right, pulling the right.
Repelling. Okay. What's going on between 2 and 3? Attracting. It's being repelled to the right. It's being attracted to the right. Net force, total force is to the right. Good. Same scenario, different object. Tell your neighbor. Correct answer is. Everybody good with to the left? Okay, we're focusing on 3. So what's going on between 2 and 3? Attracting. Which way is 3 being attracted? To the left. Between 1 and 3? Also attracting. To the left. Good? Same scenario. Well, we have the same magnitude charge, but focusing on 1. Your neighbor?
That's helpful.
Correct answer is? Okay. Between 1 and 2, what's going on? repelling. One's being repelled that way. Okay? Okay, between 1 and 3, what's going on? Okay, when I was in your shoes, I thought that 2 would run interference, like do a screen or something, like block it out. Okay, because it gets in the way. That's just like the same thing as me taking this stapler that has the force of gravity acting on it, and when I put it over the table, I'm like, wow, I just like changed how much it weighs. Like, because I'm separating something between this and the earth. Like that's running interference. Doesn't affect it at all. You okay with that? Okay. So you just ignore. Ignore 2. Okay. And how does the force of attraction compare to the force of repulsion? Less. Why? Distance. It's farther away. Okay, so the left force wins. It's stronger. Good? Okay? So now, same scenario, but now you don't know the magnitude of the charges. Tell your neighbor what you think. Tell them why you think it.
Why? It's like choosing all of the above. It's always. It's like you can always part right.
One circle. But this is the third one.
This might be the third. Straight line. Do you remember the one that I actually got like 100 on that, so I was pretty impressed. But like for like 5 days, I was like C. And I was like,
The last test had
yeah.
I'll make it.
I bet you just use it out. I think I did the Spanish finals right now.
Yeah, wide open.
All right. What do you say? Is it possible? Okay, so we had, I shouldn't erase that. We had this scenario last thing with the equal magnitude. Is it possible to make this charge big enough to make that force stronger than that force? Mathematically, yeah, sure. I make this charge strong enough, that's going to make that win. Okay? So it can't be determined. Because it could. Might not be, though. It might cancel out. Yeah. Good with that? Okay. So, on these problems that have more than 2, what you're going to do is take it just like we've been doing. We've taken it in pairs. Okay? Focusing on object C. So, I'm going to find the electric force between A and C. And then I'm going to find the electric force between B and C. And then find the resultant of those 2 forces. Okay? So exactly what we've just been doing. So I'm using this equation. Okay. So between A and C, got 8.99 times 10 to the ninth, times 10 to the ninth. Q1 is 14 times 10 to the negative 6 coulombs. I need to convert your microcoulombs to coulombs, and I'm going to drop out. Okay. Convert that to coulombs, and I drop the negative sign, and then I need 7 times 10 to the negative 6 coulombs. All over the distance separation. Make sure you square that. That is 3.5 newtons. Okay. And what's going on between A and C, attraction and repulsion? A and C, oppositely charged, so we are attracting. That. Okay. I'm going to do the same thing between B and C. Find that to be 2.8. Thumbs up when you're ready to have a conversation. All right, most everybody can get to these points here. Okay, if you didn't, you probably forgot to square the radius. Okay, but what you do with those numbers, oh my goodness, it is all over the place. Okay, and you will have a problem on this, like on the test. Okay, so here's what you do, just like what we've been doing. What's going on between A and C? Attraction or repulsion? Attraction. Which way is C being attracted? To the right or to the left? Being attracted to the left. Okay. What's going on between B and C? Attraction or repulsion? Repulsion. Which way is C being repelled? To the right. To find the net force, the net electric force, am I going to add or subtract those numbers? I am subtracting them. Why am I going to subtract them? Because one's going to the left, the other one's going to the right. They're going in opposite directions. Okay? So I'm subtracting them. Answer is 0.7 newtons to the left. That's my answer. Here are popular wrong ways, or like don't include positive, negative signs on the charge. Drop those. Those do not belong in the math. Okay. Attraction does not equal positive force, and repelling does not equal a negative force. That's another popular wrong way to interpret. No attraction, it's like come together, it's positive. Repulsion's like bad, like we don't, like no. Okay, we're talking about right and left. Okay, or up and down. Okay. Good with that? Okay. Determine net force by the direction of the forces. Determine the net force by the direction of the forces. Okay? Does that make sense what I'm trying to communicate there? Okay. So, good? Okay. You are now equipped to do the entire worksheet. Okay? Good for this to go away. Okay, we're not done though. Okay. Not done. We're not done. Hang tight. All right, check this out. Cool point of reflection here. There are 4 fundamental forces that we know of in our universe. Okay? It's gravity, we're down with that. Electric force, attraction, repulsion, strong force, weak force. Okay? We're learning about this. Strong force and weak force, these happen within the nucleus of an atom. Where do protons live? Nucleus. Right next to neutrons and other protons. Protons, aren't they all positively charged? Why do they live so close to each other? Wouldn't they want to repel? The neutrons, they're like, come on guys, can't we all get along? Like, they're like Switzerland. It's the electrons are like staying there. Nope. What it is the strong force. Strong force only happens when you're like super crazy close together, like atomic level close. So there is still a force of repulsion between the protons, but the strong force is an attractive force that's even stronger, hence the name, than the electric force of attraction. Okay? And so there's a lot of potential energy associated with the strong force. And so if you break open a nucleus due to fission, that releases a lot of energy, like nuclear bomb type energy. You good with that? Yep. And then the weak force is also another like subatomic force that only happens at really small, short distances. Okay. Now, couple points of appreciation. 2 of the 4 fundamental forces. Let's do, yeah, okay. So last semester when we were drawing fundamental, our free body diagrams, we had gravity, we're good with that. Then we had like applied force, normal force, friction, tension, all that stuff. All those other forces are actually an application of electrical force of attraction or repulsion at a molecular level. Any contact force is actually attraction or repulsion. So when I am touching this desk at a molecular level, the molecules of my finger are repelling the molecules of the desk. And that repulsion, molecules to molecules, is this cascading, I feel pressure. My nerve endings are sending signals saying, hey, you're touching something. But really, it's just like 2 magnets. Cool with that. So like, when you're a kid, you're like, I'm not touching you, I'm not touching you. Like, you get I'm not touching you, you still get in trouble. But then people are like, well, what happens if you get stabbed or something? Like, how does that, well, the molecules of the knife are strong enough to it goes in, it just pushes your other molecule, your skin molecules apart. You're not ripping molecules, you're just pushing them aside. Make sense? Okay. So, okay, another point of appreciation. Gravity. Electric force. See any similarities? It's crazy. It doesn't have to be that way, but it is. And it's a really good thing, because if this was part of the first, electrons and protons wouldn't be held together and gone. If this was R to the 2.1 power, there'd be too much force, and we're no chemistry could happen. Life gone. Okay. Some other things. The ratio of mass of protons to electrons. If they were any slightly bit off, atoms can be held together. No life. This ratio of protons to neutrons. If it wasn't just so, no fusion would happen. No suns, no stars, no life, gone. Whew! Man, I am so glad we're here. It's crazy how that happened. Well, that, more appreciation for you. All right. Take that one on. Thumbs up. You got something? I am doubling the charge and switching the sign. Tell your neighbor. Correct answer is Correct answer is B. Good with that? Correct answer, or tell your neighbor. Correct answer is E. Are we good there? Squaring the radius, squaring the distance. Thumbs up when you have something. Have a conversation. Correct answer is. Correct answer is D. Okay, check it out. We're gonna say this one has a coefficient of 1. Let's make that our standard. Okay. This guy has a coefficient we're squaring the distance. So this is 2 over 4, so 1/2. Right with that? This one four over 4. 1. Good. Okay. Last thing. Turn you loose. Here's how lightning works. Okay, so in a thunderstorm with a lot of turbulence, we're ripping electrons off of molecules in that turbulence. Okay, for reasons we're not sure why, but this happens more often than not. Electrons are on the bottom side of the cloud. which causes the electrons in the ground to run away. Okay, so these electrons in the cloud are not really, they're not like in a scenario like we've got to go to better lands. Let's go. So we're going to send out some scouts. So they start looking. These are called step leaders. Okay, you don't see these. Okay. You know how I've been preaching to you hard that electrons are the only thing that move, protons don't move? Okay, that is true in solids. But if they're liquid and gases, the molecules themselves move. You okay with that? So we're moving the whole molecule. So if the molecule is moving, so do the positive charges. They're in the house. We're moving the house. You okay with that? Okay. So air molecules lose their electrons to the ground and they become positively charged. And they start going up towards these are known as streamers. If one of these streamers and one of these step leaders connect, then like the road is connected, like bridge is happening, like things start happening, okay? You don't see this. This is what you see. When it connects, this is like the light turning green at a stoplight. The cars nearest the stoplight go first, okay? These rushing electrons, that is what produces light. If you remember from chemistry, if you excite an electron, it jumps up to a higher orbital state, and then when it falls back down, it produces light. Yes, a photon. Okay, so we're producing light with these rushing electrons. And so it looks like, because they have to wait their turn, it looks like the light is going from the ground up, but in reality, electrons are going from the cloud down. Cool with that? Okay, this next video is going to say everything I just said. It's just going to put it with some pictures.
Inside the cloud, 5 miles. A spurt of the electron rushes outwards, travels 100 meters, then stops and cools for a few millionths of a second. Then the stream lurches off in a different direction, cools again and again. Often the stream branches and splits. This is not lightning bolt yet. It's called a stepped leader, an intensely charged channel leaping and branching down. As it gets close, its electric field begins to exert a pull on the ground.
When that step leader is within 10 or 100 meters of the ground is now aware of there being a big surplus of negative electricity which has come down on a conductor. Certain objects on the Earth respond by launching little streamers up toward the step leader. Weakly luminous plasma filaments, which are trying to connect with what's coming down. If you happen to be standing there, maybe a streamer is going to leave your head and head toward that step leader. A telephone pole might launch a positive streamer. A blade of grass might launch a positive streamer up toward the step leader. It's that special one which makes the connection, which gives rise to the return stroke, and then this catastrophic 10,000 ampere current flows. That closes the switch.
When that connection is made, the electrons drain to Earth in a blinding bolt of light. The part of the channel nearest the ground will drain first, then successively higher parts, and finally the charge from the cloud itself. So the visible lightning bolt moves up from ground to cloud as the massive electric currents flow down.
Okay, good with that?
Pins as a
Okay, so this is slow motion. You don't see this. We did this with a camera that you can see it. But these are the step leaders. The lightning bolt. Okay. So I'd say this happens like a tenth of a second. Okay. The forks that you see are the electrons going, hey, we found the way. Oh yeah, this way. Good with that? One last time. Watch how the light goes from the ground up. Good with that. They're lucky to be alive. I'm not sure why they're standing out in the middle of a field. Whatever. All right. 10 minutes remaining. Use it as you need to. Lab quiz tomorrow. Worksheet due tomorrow.